In this video, we're going to be talking about solving polynomial inequalities. So a polynomial inequality means that when you multiply this out, you'd end up with a polynomial, right? Polynomials are coefficients and variables taking powers, and the powers have to be whole numbers, and there aren't any rational expressions in a polynomial. And the way we're going to solve these polynomial inequalities is going to be similar to the way we would solve an inequality in two variables. Meaning, first we have to find some critical points, and then we're going to test to see where it's true and false. So we have this inequality, x minus 2 times x plus 4 greater than 0. And when you multiply that out, you would actually get a quadratic. You would get x squared plus 2x minus 8. Right? That's a quadratic if you multiplied that out by foiling or doing the box method. And we know quadratics look like this. They could be concave up or concave down, so smiley face or frowny face, depending on if the leading term is positive or negative. But they have this U shape here. And what this inequality is asking is it's asking us what are all the x values such that the y's are greater than 0. So y is going up and down. So where's the y greater than 0? I'm going to pick a different color here. So y greater than 0 is going up, right? Anything below that line, the y values would be negative. So what are all the x values of our equation where y is greater than 0? Well, over here of our graph, those will all be greater than 0. And over here, those will all be greater than 0. Now, how do we find what those values are? We need to find these intercepts of the graph. Those are what we call critical points. So first I have to solve the function, or solve the, polynomial x squared plus 2x minus 8 to figure out where it would equal 0. And those are those x-intercepts or the critical points of our graph. So how do we solve something like this? We would factor it, which it was already factored here, and we set it equal to 0. Set each factor equal to 0 using the zero product property. So I just multiplied this out so you could see it was a quadratic. You won't take that step in your process here. I just wanted you to see it would be a quadratic. We already had the factored form here, so we set each factor equal to 0 and solve for x to find the critical points. So I add 2, subtract 4, and the critical points are at 2 and negative 4. And so again, when I say critical points, I mean the intercepts, the x-intercepts of that graph. And now I need to determine where the graph is, or the f of x values are greater than 0, where the y values are greater than 0. And if I didn't have a picture of the graph in my mind, so I knew that this would be concave up because the leading term was positive, we found the x and y intercepts, and so we can visually see where it's going to be greater than 0. But if I didn't have this picture, I can find it algebraically by testing. So we have this number line. Negative numbers go down, positive numbers go up. And we can see there's going to be 3 regions of our graph, or of our number line, based on where those critical points are. And each region is either going to be true or false. The whole region is either going to be greater than 0, or the whole region is not going to be greater than 0. And so we have to test a number in each area. Not the critical points. We have to pick a different number in each area to test. So looking over here to the left, I'm going to pick negative 5. I don't want to pick huge numbers because I want to keep the math simple for myself, but the next whole number down after -4 would be -5. So I test. I'm going to let x equal -5. If I plug it into my original equation, because I haven't changed anything, I wouldn't have made any mistakes yet, so that's why I use the original. I want to know if I end up with a true or false statement. So -5 plus -2 is -7, and -5 plus 4 is -1. A negative times a negative makes a positive. Is 7 greater than 0? That's true. If it's true, I shade that region. So this is going to be part of my solution set. And I'm going to not include the -4 because this was strictly greater than 0. It doesn't say equals 0, it says greater than 0. So to not include -4, I'm going to use a parenthesis or an open circle. And that's where we see this value, or these values here. All of these values are going to get wider and move left forever, and that's why it's going left forever. I test the middle area. So I'm going to test something between -4 and 2. The nicest value that I can think of would be 0. Plugging in 0 for x into my original inequality. So now I have -2 times a +4, and I get -8. Is -8 greater than 0? That is false. If it's false, it's not part of my solution set. I don't shade. And then lastly, I need to test this last area. So something bigger than 2, I'm going to test 3. So let x equal 3. Plug it into my original inequality. I have 3 minus 2 is 1, and 3 plus 4 is 7. 1 times 7 is 7. Is 7 greater than 0? That is true. So everything on that side is going to be part of my solution set. And I do not include 2 as part of my solution because it was a greater than and not greater than or equal to. If I want to write this in interval notation, I just read my graph from left to right. So starting at -infinity up to -4, union starting at 2 and going up forever. And those are all the values such that x minus 2 times x plus 4 is greater than 0. Again, visually this is what's happening. Algebraically this is how we can test it, and this is the final solution. Go ahead and try the examples on the right. So in this one you would have 3 terms that you're going to, or 3 critical points you're going to have to look at. This one you would need to factor first before you solve for those critical points. And this one is not set greater than or less than 0. So you should get everything on one side first and then try to factor. So try those 3 and see how you do. Alright, let's see how you did. Looking at this first example, it's already factored. All the variables and constants are on one side, set less than 0. Once it's factored, we identify the critical points by setting each factor equal to 0 and solving for x, essentially finding the x-intercepts. So solving each one, I get x equals 2, x equals -1, and x equals -5, just by adding 2, subtracting 1, and subtracting 5. So those are the 3 critical points. I'm going to go ahead and make a graph here with -5, -1, and +2 as our critical points. We have to test each area, so each region. I have 1, 2, 3, 4 regions I need to test. So I'm going to start with -6, because that's less than -5. I'm going to let x equal -6 to test. I'm going to plug it into my original. So -6 minus 2, -6 plus 1, -6 plus 5. Is that less than 0? So I'd have -8 times a -5 times a -1. When we simplify those parentheses, 3 negatives will make that negative. 8 times 5 is 40, times 1 is still 40, so -40. Is that less than 0? True. Negatives are less than 0. So this whole region is part of my solution. And because it was strictly less than, it's not equal to, I'm going to use a parenthesis or an open circle, open point. All right, let's test another one. Let's do in between -5 and -1. I'm going to try -2. Trying to keep my numbers smaller so it's easier to multiply and such. So I'm plugging in -2 for x. Everywhere I see an x into my original inequality. Alright, I would end up with -4 times a -1, which is +4, times 3, which will be +12. So is +12 less than 0? That's going to be false. So that's not part of our solution set. Now I'm going to test something between -1 and +2. So since it's switching from negative to positive, I know 0 has to be in there, and 0 is a nice, easy point or value to pick. So 0 minus 2, 0 plus 1, 0 plus 5. Is that less than 0? Well, 0 plus anything is 0, so I'd have 0 plus anything is itself, so I'd have -2 plus 1 is -2, -2, sorry, not plus, -2 times +1 is -2, and -2 times 5 is -10. Is -10 less than 0? That is true. So everything in this region is going to be less than 0. I do not include 1. I do not include 2. And then lastly, something in this last region greater than 2, I'm going to pick 3. 3 minus 2, 3 plus 1, 3 plus 5, less than 0. I'd end up with +1 times 4, which is 4, and 4 times 8, it's going to be 32. Is 32 less than 0? That is false. So that's not part of our solution set either. In general, it will go true, false, true, false. So most of the time, that's the pattern you're going to get. What's happening visually, whoops, make that bigger again. So visually what's happening is this is not a quadratic because there's 3 x's here, it's a cubic. So it's going to go up and down and up. And so that's why there's 4 regions. Maybe I should make it more prominent. Down and up. And we're now looking for values that are less than 0, where the y values are less than 0. So where is it less? Down here, that's less than 0. And under here, that's less than 0. And then that's it. So that's why we get this to infinity to the left here. And then this value here from -1 to 2. And then these values are greater than, so that's why they're not included. That's why it switches. So every time we cross the x-axis, it's switching from greater than or less than 0. So this is less than 0, now it's greater than 0. This is less than 0, now it's greater than 0. And so that's why in general it's going to go true, false, true, false, true, false, true, false, and so on. But that's not always the case. So do not assume that that is what's happening. Because what could happen is you could have a graph that goes through and then bounces off that x-axis. Or you could have a graph that doesn't cross it again. So you need to be testing these values to know for sure whether or not it's part of the solution or not part of the solution. So for example, this one would only have one region that was less than 0 because everything else stayed above that x-axis. So again, please test all your regions to know whether or not it's part of your solution set. Let's write this in interval notation now. So starting at -infinity up to -5, and then union -1 to 2. I'm going to do it in a different color so we can see it. So -infinity up to -5, union -1 to 2. That is our solution set. Alright, let's look at this next example here. It's already all on one side, so set greater than and equal to 0, but we have to factor. So we are looking for factors that will multiply to -30 and add to -1. I'm thinking 5 and 6. One of them has to be negative, and that needs to be the 6, so it will add to -1. Now my leading term here is not a 1, so I cannot set these into my factors. I have to rewrite the middle term using these and factor by grouping. I'm going to go ahead and do that over here so I leave some room for the rest of the problem. Alright, so let's factor it. I have 10x squared plus 5x minus 6x minus 3. We're solving it for the intercept, so I'm just going to set it equal to 0 so we can see that. I'm going to factor by grouping, so I group the first two and the last two. The GCF on the first two is 5x. I pull that out. I'm left with 2x plus 1, right? 5x times 2x would be 10x squared. 5x times 1 would be 5x. The GCF on the second set would be -3. I'd be left with a positive 2x and a positive 1 when we divide out -3. If I did it right, these should match, and they do. So now that's the GCF, and I'm going to pull that out, and I'm left with 5x minus 3 when I pull that out. Now I can set each factor equal to 0 to find the intercepts or the critical points. I would subtract 1 and then divide by 2 to get -1/2 on the first, and I would add 3 and divide by 5 to get 3/5 for the second. So those are the critical values. -1/2 and a positive 3/5. Now just because we found fractions here, we can still pick whole numbers to test. We don't have to pick fractions just because our critical points were fractions. So now, something less than -1/2, I'm going to pick -1. Right? -1 is further left on the number line than -1/2. So 10 times negative 1 squared minus negative 1 minus 3. I want to know if that's greater than or equal to 0. Notice I went back to the original because I haven't made any errors yet. I haven't made any factoring errors or anything that could be possible. I'm going to go back to the original where it's not messed up yet. I'm not saying I did mess up, just being safe by going back to the original. Negative 1 squared is positive 1. So I have 10 times positive 1, which is just 10. And minus negative, when we subtract a negative, it becomes positive 1. So I'll have 11 minus 3, and I'll get 8 is greater than or equal to 0. Is that true or false? That's true. Okay. So that means that everything left here is part of my solution set. And because I have this equal to bar, I'm going to include negative 1/2 in my solution set with a bracket or a closed point. Now I need to test something in between these two values. Well, again, it's changing from negative to positive, so I know a 0 has to be in there somewhere. So that's an easy value. Plugging in 0 for x. 0 squared is 0. Anything times 0 is 0. So I end up with negative 3 greater than or equal to 0. True or false? False. Negative 3 is not greater than 0. So this is not part of our solution set. Lastly, I need to pick something over here. 3/5 is less than 1 whole, so the next whole number would just be x equals 1. So I'm going to try x equals 1 into my original inequality. 1 squared is 1. 10 times 1 is still 10. Minus 1 minus 3 would be positive 6. Is positive 6 greater than 0? That is true. So everything going up from here is part of my solution set. Again, because of that equal to bar, I will include 3/5 as part of my solution set. If I wanted to write this in interval notation, I'd read my graph from left to right, starting at negative infinity, going up to negative 1/2, and including it, union from 3/5 up to infinity. And again, what's happening here visually is I have a quadratic equation with a positive a value, so it's going to be concave up. And I'm looking for all the values greater than or equal to 0. So all of these values and all of these values are where f of x is greater than or equal to 0. And that's why we end up with these two regions here that are part of our solution set. One more. X squared minus 2x less than or equal to 2. So everything is not on one side. I need to get it on one side. I will subtract 2 from both sides and end up with x squared minus 2x minus 2 less than or equal to 0. Do you want to predict what the region will look like? If I were to draw a graph of this quadratic function, x squared minus 2x minus 2, a value is 1, so it'll be concave up, it'll be facing upward, and I want all the values, all the y values that are less than or equal to 0. So that means all these values down here are below the x-axis. So I think I'm going to end up with just one region that works, that is true. But let's find out. First I have to factor. So I want something that will multiply to negative 2 and add to negative 2. The only factors of 2 are 1 and 2. If I try to put a negative somewhere, it's not going to add to negative 2. So this looks like it's not factorable. Alright? What do we do if it's not factorable? We have to solve it using the quadratic formula. So if I want to find those intercepts here, where does it intersect that x-axis? I have to use the quadratic formula. X equals negative b. Negative b would be negative 2, which is positive 2, plus or minus the square root of negative 2 squared minus 4 times a times c, all divided by 2a. Negative 2 times negative 2 is positive 4, and then negative 4 times 1 times negative 2 will be positive 8. So we have 4 plus 8 under the radical, which will be square root of 12. And 2 times 1 is 2. We can simplify that radical by taking out our perfect square. The square root of 4 is 2, so we'll have 2 square root with 3 left under the radical. Now I can keep simplifying because I notice that all 3 terms here have a factor of 2, right? 2, 2, 2. I can divide them all by 2 and get 1, which means I'll be dividing by 1, and I'll just end up with 1 plus or minus the square root of 3. Now, since I'm going to be drawing a number line, and I need to figure out where these critical values are on the number line, I'm going to go ahead and approximate these as decimals. So I'll leave the exact answer as my final answer, but for the sake of my number line, I'm going to approximate. I'll have the positive square root of 3 plus 1 is about 2.7. And the negative square root of 3 plus 1 is negative 0.7. Okay, so somewhere in the middle I'll put a 0. That's not a critical point. And then about 2.7 is the positive radical, so 1 plus the square root of 3. And then about negative 0.7 is the negative radical, so 1 minus the square root of 3. So those are our 2 critical points. And now I'm going to test each region. So I'm going to go ahead and test x equals negative 1, since that is further left on my number line than negative 0.7. I'm going to plug it into my original to test it. So negative 1 squared minus 2 times negative 1 less than or equal to 2. Negative 1 squared is positive 1, and negative 2 times a negative 1 is positive 2, so I'll have 1 plus 2 is 3 less than or equal to 2. That's false. This is not part of my solution set. I'm going to test 0. That's a nice value in between, so in this middle region between my 2 critical values. If I plug in 0 for x, I'll have 0 squared minus 2 times 0 less than or equal to 2. The left-hand side is all 0. Is 0 less than or equal to 2? That's true. So this whole region here is part of my solution set. And because I have this equal to bar, I will include those values in my solution. And last, I need to test the last region, which is something greater than 2.7, so I'm going to pick x equals 3. 3 squared minus 2 times 3, is that less than or equal to 2? I'll have 9 minus 6, which will be 3 again. Is 3 less than 2? No, that's false. So again, not part of our solution set. So just knowing a little bit about graphing quadratic equations and the fact that I wanted less than, I knew that I'd have one region. So when I got it all on one side, I wanted to know when that function was less than or equal to 0, and that was down here below the x-axis, and I ended up with just one region in between those two critical points on my number line. So the final solution would be an interval notation from 1 minus the square root of 3, so that was our smaller value here on the left, up to 1 plus the square root of 3, and including both of those with brackets in my solution set. And there you have it. So to solve polynomial inequalities, we need to get everything on one side, set it less than or greater than 0, factor it. If it's not factorable, we can use the quadratic formula to find our critical points, also known as the x-intercepts. And then we test each region to know whether or not it's part of our solution. And if you're good with graphing, you can also use this as a second method to know whether or not it's less than 0 or greater than 0. And then be sure to remember when to use brackets and when to use parentheses.